So welcome to the last lecture of Laplace transform, and we're going to talk about the stability of a system. We have learned about in the last video how to find out h of s, and after we find out our transfer function, if we do inverse Laplace transform of our transfer function, we're going to come back to our system's impulse response. And we know system is stable only if our impulse response is absolutely integrable. That means its integration from minus infinity to infinity should be bounded. So the definition of Bibo stability is going to be that our system response should die out at the infinity, as it has to be absolutely integrable, so it must die out at infinity, so its graph should look like this. And if system is unstable, if it is unbounded, system is unbounded, so that means it's going to grow slowly. So that means at infinity time its value is also going to be infinity, and system will be marginally stable if st is either a constant or it is oscillating in nature. So that means if st shares a form like 5 or cosine of 3t, then we'll call that marginally stable. In this marginally stability case, it's not fully stable at infinity, it doesn't die out, and also it's not unstable, it's not infinity at the time infinity. So that's the definition, that's three basic definitions. Now we'll define something for causal systems. For causal systems, we don't want to do inverse Laplace transform and then find out whether it's going to be absolutely integrable or not. We want to see the poles only, and then we want to decide whether the system will be stable or unstable. Okay, so this whole discussion is about causal system right now. So for causal system, there is going to be some numerator, and according to our partial fractions rule, there is going to be some denominator which can be expressed in this fractionized form. There can also be some irreducible second order factor which we are neglecting for now. So we'll be focused on first order factors only. So which there is going to be some factors, and according to our partial fraction rules, we can make one separate terms for each factors, and for repeated factors there are going to be repeated terms till we get to the power of our repeated factors. So you see, when you do inverse Laplace transform for the pole s minus a, our answer is going to be e to the power at ut. For the term s minus v, our answer is going to be e to the power bt ut times something which is not important. For s minus c square is going to be e to the power ct ut times t, because it's a derivative of 1 by s minus c. So taking derivative in s domain means multiplying by t in our time domain. So now try to understand for a or slash b, that means either for a or either for b, for non-repeated poles, if they're positive, that means e to the power positive something times t. So at infinity it's going to have infinity value, so it's unstable. And if it is negative, it's going to die out at infinity, so it's going to be stable if our pole is negative. And if our pole is imaginary number, then it's going to be like e to the power j3t. So that's by Euler is cosine 3t plus j sine 3t, and that's oscillating in nature, and then it's going to be marginally stable. Now if our c is negative, that means if our repeated pole is negative, then we will have a stability, because e to the power minus t, e to the power minus kt dies out faster than our just t. Alright, and but in other case, if c is positive, then obviously t times e to the power kt, whether case 5 6, then it's going to be infinity at the value of infinity, so it's going to be unstable. And also if our c is imaginary, then also it's going to be unstable, because t times sine omega t, and because t times e to the power j3t, let's for example, so is going to be cosine of 3t plus j sine of 3t. Although this is bounded by 1 and oscillating in nature, but there is a t here, so it's going to gradually increase its amplitude, and it's again going to be unstable. So the thumb rule is that for causal systems, if you have non-repeated roots, then if they are positive, it's obviously unstable. If their pole is positive, it's obviously unstable. If the pole is negative, it's stable. If the pole is imaginary, then it's marginally stable. And for repeated roots, it has to be, the pole has to be negative to be stable, otherwise it's going to be unstable. Very clear cut definitions. Alright, so first question we're going to answer is, it is asked to check the stability of our causal system. So we know what h of s is going to be. It's a negative feedback system, so it's going to be 1 by s plus 1 divided by 1 minus plus 1 by s plus 1 s by s plus 2. It's a very common system. When you simplify it, it's going to be s square plus 4s plus 2, right? And yeah, that's how it is going to be. And if we try to check out its if we try to find out its values, find out the poles, then it's going to be s plus 2 divided by, if we try to find out the poles by using our formula of quadratic equation minus b plus minus root over b square minus 4ac divided by twice a, then it's going to be ultimately minus 2 plus minus root 2. So it's going to be minus 2 plus root 2, which is also negative, or minus 2 minus root 2, which is also negative. So both the poles are negative, and if the poles are negative, we're on the safe side and the system is stable. So that's going to be our answer. We can determine the stability of a causal system just finding out these roots of our poles of our denominator. Now we want to solve a different sort of problem. It's given that the hs is like that, 1 by s plus 2 plus 2 by s minus 3, and we know that the system is stable. Then what is h of t? It's not given here that the system is causal, so it doesn't have to be ut at the end, but it is given that the system is stable, so ht is always decaying, it's not infinity anywhere. And we want to find out what is the form of ht, whether it is causal, non-causal, or anti-causal, or whatever. Now 1 by s plus 2, there can be two forms, whether it is causal. If it is causal, we don't know the ROC, so there can be two sort of inverse Laplace transform. If it is causal, then it's going to be e to the power minus 2t ut, and if it is non-causal, then it is going to be minus e to the power minus 2t e of minus t. And 2 by s minus 3, if it is causal, it's going to be e to the power 3t ut, and if it is non-causal, it's going to be minus e to the power minus 3t e of minus t. Now this is e to the power minus 2t, a negative factor, a negative exponential, and it's going to die out for positive time period, but it's not going to die out for the negative time period. So if it has to be stable, if ht has to be stable, then s plus 2, so that means minus 2 needs to be a causal pole. Now e to the power 3t, e to the power 3t really becomes infinity in the positive time, but it dies out in the negative time. Alright, because e to the power minus 3t slowly becomes 0 in the time, as the time decreases, in the negative time. Alright, so if the system is stable, then if the system is stable, then if the system has to be stable, then s equals to 3. That means 3 has to be an anti-causal pole. So our inverse Laplace transformation will be e to the power minus 2t ut minus e to the power 3t u of minus t. So as this was a causal pole, so our answer should be real part of s is greater than minus 2, the ROC for this pole, and the ROC for this pole has to be real part of s is less than 3. So our ultimate ROC should be the intersection, so the ultimate ROC is going to be this. And that's not the important point. The important point is that you shouldn't confuse yourself between this causality and finding out HT on the basis of stability. When it is said on the causal system, you just find out the poles and you see whether the poles are negative or not, and you can tell out your stability. But when it is said that it is stability, you should immediately forget about the causality. There is no sign of causality here. It can be both causal and non-causal, but you should try to see whether which pole should be causal or which pole should be non-causal to make the system unstable, and according to that you build up your system impulse response, and according to that you find out your ROC. So that's all for Laplace transformation. Our application has been covered. I've tried to make things simpler, and in there I have followed some hierarchy. I've first covered how to do Laplace transformation, then covered properties, then covered inverse Laplace transformation, and then covered application. If you have any question, share or please comment and stay with us. Thank you.